Okay, so today we're talking more about angles and parallel lines. Like I foreshadowed in the last lesson, today we're talking specifically about the corresponding angles, alternate interior, alternate exterior, that when you have parallel lines, how those angles end up being congruent to each other. So we're just going to get into that a little bit more today. So I would add a little bit to your notes from last time, but you probably don't need to add a massive amount. So we're going to go through the postulates first, the postulates and theorems. They're going to be very similar to the definitions that we talked about last time. So first things first, we have the corresponding angles postulate, which says if two parallel lines are cut by a transversal, then each pair of corresponding angles is congruent. And what I love about this picture is how they section it into red and blue. So our pairs of corresponding angles are 1 and 3, 7 and 5, 2 and 4, and 8 and 6. And of course, those are corresponding because they share the same relative position on the same side of the transversal. So 1 and 3 are top left above the transversal and on the left hand side. 2, 4 are above the transversal on the right hand side, so on and so forth. But why I love that they used red and blue here, let me erase real quick and I'll show you what I'm talking about, is that in general, we can make a generalization when we have two parallel lines cut by one transversal. And that generalization is that all the obtuse angles are the same and all the acute angles are the same. Obtuse in this case being red and acute being blue. And so why this works out is because if we start with angles 1 and 3, we said that they are corresponding. And so they're congruent by definition. They have to be congruent. And if we go back to angle 1, I could say that 1 and 5 are also the same because they are alternate exterior angles. And then using angle 5, I could say that 5 and 7 are in fact congruent based on corresponding angles again. So we can say that all the obtuse angles are congruent just by looking at them right away. And if we had to do a proof, which I wouldn't anticipate, but just in case, we could use those definitions I just ran through. 1 and 3 are corresponding, 1 and 5 are alternate exterior, and then 5 and 1 are, or I'm sorry, not 5 and 1, 5 and 7 are corresponding. So therefore, by the transitive property, all of those are congruent together. So all our obtuse angles are going to be the same, and we can use the same process to determine that all the blue angles are the same, all these acute angles. So 2 and 4 are congruent because they are corresponding angles, and then we could say 2 and 6 are congruent because they're alternate interior. They both lie inside the parallel lines and on opposite sides of the transversal. And then we could use 6 and 8 and say, well, they're corresponding as well. So based on the following process, we can say, well, all the acute angles are the same. And there's going to be a lot of problem-solving problems with this where you're supposed to determine different angle measures or solve for variables. And the important thing to remember in that case is that one of the acute angles and one of the obtuse angles, so one of the blue and one of the red, are always going to add up to equal 180 degrees. And we can tell that based on, if we look at angle 1 and angle 2, they form a linear pair. Angle 1 and 8 form a linear pair. Angle 8 and 7 form a linear pair. 3 and 4 form a linear pair. 3 and 6 form a linear pair. 4 and 5 form a linear pair. So all of these individual angles add up to equal 180 degrees, which makes it, I don't want to say easy, but it makes it quick for us to justify their individual angle measures based on our generalizations, that all the obtuse and all the acute are going to equal each other. So moving on, we get into alternate interior angles theorem, which we touched on last time. But just as a quick review, what that tells us is that if you have two angles that both lie on the inside, which the inside is the area between the parallel lines, and on the opposite side of this transversal, I don't know why I selected the highlighter there, but you know what? That's what we got. So if they lie inside on the interior and then one on top of the transversal and one on the bottom of the transversal, then they end up being alternate interior angles, such as angles 2 and 4 or angles 1 and 3 in this situation. And this is always true as long as you have two parallel lines cut by a transversal. I'm going to skip consecutive interior angles theorem right now. We'll come back to that shortly, but I want to touch on alternate exterior angles theorem because it's so similar. So like before, we had the yellow was our inside, and then our green is the outside or the exterior of these parallel lines. So when we have two angles that lie on the exterior, one on top and one on bottom of our transversal, such as angles 8 and 6, then we can also say that they are in fact congruent based on alternate exterior angles theorem. And we could do the same with 5 and 7. So if they are both on the exterior, one on top of the transversal, one on bottom of the transversal, then we can say they are congruent. And if we look at this again, just a quick refresh, 5 and 7 are both acute, 6 and 8 are both obtuse, so our little rule of the obtuse angles are the same and the acute angles are the same continues to ring true in this situation. So now consecutive angles theorem. What consecutive angles theorem says is if two parallel lines are cut by a transversal, then each pair of consecutive interior angles is supplementary. So our interior, once again, we'll label as yellow. And this one I find less useful, and we're not going to see it nearly as much for that reason. So if we have on one side of the transversal, which let me draw that in just a little more clearly with the black marker. So if we have two of them on the inside that are the same, on the same side of the transversal, both on the interior, such as angles 1 and 2, what this says is that they are supplementary. They add up to equal 180 degrees, which we know because we have one acute, one obtuse. So they're going to add up to equal 180 degrees in this parallel lines cut by a transversal situation. Like I said, consecutive interior angles theorem, you're not going to see as much. It's important to know just in case there's a random test question or a random question on your state test, but it's less useful. So going into our actual application problems. So in this example, they say in the figure A is parallel to B, and the measure of angle 18 is 42. So I'm going to label this as 42 degrees. They want us to find the measure of angle 22. What I want to do is find the measure of all the angles. So in the lesson, the way it's drawn up is we go through like 15 example problems, finding all these different angles using like 3 different pictures. So I just want to use those 3 pictures. Let's find all the angles and let's keep it moving. So once again, I want to use red and blue to designate which angles are obtuse congruent and which ones are acute congruent. So just for starters, I'm going to say red angles equal, and then I'm going to say blue angles equal, which I should start off by saying that this isn't really the highly mathematical way to do it, but if we can do it this way, then I know we can take these answers and snazz them up and make them all mathematically happy. So let's go ahead and let's start with the blue angles because they gave us our acute angle. 18 is an acute angle, and they said it was 42. So right away, I know all my acute angles in this situation are going to be 42. So I'm going to write 42 degrees here. Before we move on to the red angles, though, what I want to do is I want to go through and highlight every single angle and why we can say that it is 42 degrees. So I'm going to start off with our corresponding angles. So 18 corresponds to 22 because they're on the same side of the transversal and share the same relative position. So we know 22 is also 42 degrees. So I'm just going to label that as blue. Going back to angle 18, I can use alternate exterior angles to say that 25 is also 42 degrees because they lie on opposite sides of the transversal and both of them are in the exterior. The other angle that we can use is angle 21 is also going to be blue, and I'm going to base that off of 25 and 21 are corresponding angles, so they share the same measurement because they both lie on the same side of the transversal, and then they share the same relative position. We could also say that they're alternate interior angles, 21 and 22, to say both of them are 42 degrees as well. So that labels all of our acute angles in blue, and we know all our blue angles are 42 degrees. So if this was a test question, what we would say is, okay, angle 22 equals 42 degrees. But I want to use this more as an understanding tool and less as like a let's answer a random question tool. So our next step would be to highlight all of our obtuse angles. Right away, I see 19 is an obtuse angle. So I'm going to circle 19. I know 19 and 24 are the same because they're alternate exterior. 19 and 23 are the same because they are corresponding angles. And then I can say 20 and 24 are going to be the same because they are corresponding angles as well. Now comes the tricky business of finding out exactly what those red angles or our obtuse angles equal degree-wise. So what I'm going to do is I'm going to highlight just this top bit here. So this and this. So we have two angles that added together equal 180 degrees. So they are a linear pair. And I can solve this linear pair. So I know angle 18 plus angle 19 equals 180 degrees. And I know angle 18 equals 42 degrees. So I'm going to substitute in 42 plus angle 19 equals 180. And then I'm going to solve it for angle 19. So I'm going to subtract 42 from both sides. And I'm going to find out that angle 19 equals 138 degrees. 138 degrees. So I can safely say that all my obtuse angles now are going to be 138 degrees, which checks out because 138 plus 42 equals my 180 degrees, and I know each of these form a linear pair. So that is how I would go about solving for all the angles. Now I know most of the time you're not going to have to solve for all the angles, but it's a good tool to have in your repertoire. So moving on to our next problem, we have a floor diagram from Michelle's house, our good friend Michelle. She has all this tile in her house. So this diagram, we have quite a few sets of parallel lines here. So I'm going to go ahead and just label these. So all of these are parallel, these ones that are kind of going diagonal left and right, and then the ones going just straight across from left to right, they are also parallel. So this one becomes slightly trickier, but it's still doable. So we're only solving for 4 angles here. So right away, let's highlight which ones are the same. So my red angles, again, I'm going to use those as my obtuse angles. And then my blue are going to be my acute. So angle 2 is obtuse, and we know angle 2 equals 125 degrees. So what I'm going to do is I am going to use my black marker, and I'm actually going to black this whole piece out because I don't think we need it. So we're just going to ignore that section and get a little bit less going on. And the other thing I'm going to black out here is this one, because I don't think we need that either, because all these angles lie in the two left to right parallel lines cut by the transversal going up and down. I'm just going to call that transversal L just for explaining sake. So right away, I know angle 2 is 25 degrees. Angle 3 is my other obtuse angle. I can tell just by looking at it, but I know they're the same degrees because they lie on opposite sides of the transversal and they're both on the interior. So by alternate interior angles, I can say that they are equal. So I'm going to say angle 3 is also 125 degrees. So if we want to label these, we can say angle 2 equals 125 degrees, and that was given to us in the first problem. And then angle 3 is also 125 degrees. So for this problem, they want us to find the measure of angle 4, which is an acute angle, and we're also going to find the measure of angle 1 just for to be thorough. So angle 1 and angle 4 are both they're both acute angles, and they're both equal to each other because they are alternate exterior angles. So they both lie outside of our parallel lines and then on opposite sides of the transversal. One's on the left side of L and 4 is on the right side of L, which is our transversal, of course. So once again, I'm going to take my black marker and I'm going to highlight a linear pair here. So I see 1 and 2. If I draw a line through them like this, and then have this angle coming up here, they form a linear pair, which, as we said last time, that means that they add together to equal 180 degrees. So I have angle 1 plus angle 2 is going to equal 180 degrees. And I know angle 2 equals 125 degrees, so once again, I'm going to substitute that in. So angle 1 plus 125 equals 180. And then if I solve that, I subtract 125 from both sides, and I end up with angle 1 equals 55 degrees. And like we said previously, so I'm going to go ahead and write this, angle 1 equals 55 degrees, and then angle 4 equals 55 degrees as well. And they're the same because of alternate exterior angle theorem. But we know when we have two parallel lines cut by one transversal that all the acute angles are going to be the same and all the obtuse angles are going to be the same. But we need to know that it's because of alternate exterior, alternate interior, and corresponding angles, just so we can justify that if we're asked to do so. But it's nice to know the general rule just to, make it a little quicker on ourselves. All right, so our last problem and our hardest problem is going to be this one. So this is an algebraic application. And so we're supposed to find out what x equals. Now this one we're just going to solve exactly like the problem wants us to. We're not going to get wild and reckless with it. So right away, I can say that all my, for angle 5 and angle 7, I know that these are going to be equal. So if I look at, I'm going to black out this whole right-hand side. All of this, because it's all garbage that we don't care about. And why that is because angle 5 and 7 are formed in this set here. So we have these parallel lines that I just colored in black, cut by, forgot an arrow there, cut by this transversal of M. And now what I can see here is that angle 5 and angle 7 are going to be the same because they are corresponding angles. They both lie on the left-hand side of the transversal M, and they're both in the same relative position. And what I mean when I say they're in the same relative position is that if we took, like if I cut, oh, it's not going to let me do that. That's fine. So if I was able to kind of take scissors and just cut out this whole top bit here, if I can get it done. So if I was to cut right like this and pick that up and set it right over in here, it would lie straight on top of it and we wouldn't be able to tell the difference, because they are the same exact thing, just kind of slid up that transversal. So anyway, angle 5 and angle 7 are the same because they're corresponding angles. So if we're going to solve for x here, what we need to do is set angle 5 equal to angle 7. So angle 5 equals angle 7. And then I'm going to substitute in my values. So angle 5 equals 2x minus 10. And then angle 7 equals x plus 15. So to solve this, I want to get all my numbers on one side and all my x's on the other side. So I'm going to add 10 to both sides. So I'm left with 2x equals x plus 25. Then I'm going to subtract x from both sides. So I'm left with x equals 25. Now, this solves the problem. We have x equals 25. Now, if I was asked to find out what the measure of angle 5 or the measure of angle 7 is, I would just take this x and I would plug it back in to either one of these equations since they are congruent angles, and I could find it out that way. So if we wanted to do that, I could plug in 25 to angle 5's equation. I could say, okay, a measure of angle 5 equals 2 times 25 minus 10. So measure of angle 5 equals 50 minus 10, which means measure of angle 5 is 40 degrees. And using that, measure of angle 5 equals 40 degrees. If we wanted to, we could go back in here and we could find out what each and every single one of these angles measure is, which we know that all our acute angles are going to be the same. So we could say that angle 4 is going to be 40, and then we could say, well, angle 4 plus angle 6 equals 180, so angle 6 is going to be 140 because they add up to equal 180. So I could say angle 6 and angle 8 would equal 140 degrees also. Of course, the problem wasn't asking for that, but we're just going a little above and beyond today. And then our last theorem, this one is pretty straightforward and easy. I don't anticipate you will ever need this, but just in case. So perpendicular transversal theorem. In a plane, if a line is perpendicular to one of two parallel lines, then it is perpendicular to the other. So what this is saying is, okay, we have our two parallel lines, it's cut by a transversal. If this is 90 degrees, then its corresponding angle is 90 degrees. Its alternate exterior angle is 90 degrees. That angle's corresponding angle is 90 degrees. So they're all going to end up being 90 degrees. If one of them's 90, they're all 90. I feel like we've covered that piece pretty good over the last, I don't know, month. If one's 90, all's 90.